Okay, very good. Okay, so we're going to finish up the electrochemical piece, and then we're going to get into the activity coefficients piece, or real solutions. And so this is the general form of line notation. So we were talking about galvanic cells. We had an anode and a cathode, and we had this cute little scheme that I drew that connected the cathode to reduction and the anode to oxidation, because you can go by the first letters, there being a C in the word reduction, so cathode goes with reduction. And there's an A in anode, so it goes with oxidation. And then we can write this out in shorthand using this line notation. So the vertical lines represent these junctions, which would be any kind of phase transition. So if you're going from a solid to a liquid, or liquid to like a salt bridge, which isn't really a solid, but it's definitely a junction. It's so concentrated that it's saturated essentially. It's mostly salt with a little bit of water. So what do you call that phase? I mean, I don't know. It's not really a solid. We would call it a slurry, something that's saturated. So a slurry, but that's enough of a phase change that there'll be a little potential set up at that junction. So these junctions are important. At this course, we don't have enough time to go in depth about these little junction potentials, but every one of those junction potentials will be a slight voltage change, and they'll affect the performance of the galvanic cell. So here's some of the fuel cells that we've seen. So it's always in this order alphabetically. So copper is the anode because it's listed first, and that silver is the cathode because it's listed last. And here's magnesium and aluminum. So these are good cells you can get voltage out of. And then here's an example where you have non-metal reactants taking place with platinum electrodes. And so then you need to, in writing out, like if you're going to study this particular cell and do calculations on it, you need to look at this and see that this is the anode, so this is the oxidation reaction. And so you would write it with the reactant being less oxidized than the product. So this is an easy one because you can look at this. The ClO4 has more oxygen, so it's more oxidized. So it's the product, and this ClO3 is got less oxygen, so it's less oxidized. And then this would be the cathode. That's where reduction takes place, and so this is the reactant, MnO4, and this is the product. Now, how would you decide? Well, you would write out the balanced reaction and look to see which side the electrons are on. So that would help you correct your mistake if you wrote this out. And so let's just try to write that out. So if we did, I don't know, this is going to be kind of tight down here, but let's try it anyway. So we have Cl, I'm down here at the bottom. I need to get away from that. There's no room on here. We'll look at another example next page. So what's the standard cell potential of this reaction? So here we have iodine and I2 and permanganate and manganese ion. So this is the order of these. And so we use the reduction potential table to find the half reactions. Now, if you have the reduction potential table, it's super easy because you just find the species in there. Now they're all written as reductions. And so the one that's the oxidation, the iodine reaction, you flip that one. And so this is the oxidation. It would be written as a reduction, so it would be written in reverse in the table. It would be I2 plus 2 electrons equals 2I minus. And so you find that in the table, you flip it, you change the sign on the voltage. And then here's the permanganate half reaction. So if you have the reduction table, you really don't even have to do the whole balancing of the redox reactions in terms of the first few steps, because they're balanced. Those half reactions are already balanced in that table. So you find them in the table, you flip the oxidation, you stick them together, and then you just have to get the electrons to match up. And so we need 5 for the permanganate, and we only get 2 from the iodide. And so we need to do 5 times the top reaction and 2 times the bottom reaction. And notice we don't multiply the potentials. I emphasized that last time. And so then we add everything up as we come down. And so this is our balanced half reaction, balanced full reaction. The electrons have canceled, and we have this cell potential of 0.97 volts. Okay, and so you just need to find the correct species in the reduction table. Be sure to change the sign of that potential for the oxidation half reaction, and you can add them together. And don't multiply those potentials by anything. So this is the fastest way. It's a very clean notation. You have this single line notation. All you need is subs and supers. You don't need any arrow keys or anything like that. And you need a reduction table. So this is a shorthand, fast way to talk about electrochemical reactions. So now let's think about the decision-making process if we wanted to find a particular voltage. So that's I would say the typical practice. If you're going to come up with a galvanic cell, you need a certain voltage. And so you can take that reduction table, and so here's your reduction potential table here. And you know that if the top reaction is going forward, the bottom reaction is reversed, then you're going to come up with a cell, so a spontaneous cell. And so if we take the 1.50 and we subtract the 0.8, we get 0.7. So that's gold going forward and silver going backwards. Okay, gives us a 0.7 volt cell. Gold going forward and copper going backwards would give us 1.16. If we took silver, so 0.8 minus 0.34, that would be the difference between the silver potential. Okay, so we just make a little table of all of these differences, and that will tell us all the possible voltages we could get out of that reduction potential table. So if we're looking at this one and we want 1.5 volts, this is perfect. A silver zinc cell would give us 1.56 volts. And that's good. You want to overshoot it a little bit. Most devices have a range of voltages that they can accept. And so all of your devices that would take a standard 1.5 volt battery would work on this. And you could just make up, if you had silver and you had zinc, if you had silver ions in solution and zinc metal, you could set those up as your electrodes in your battery, and then you could make this cell. We made a little stack of pennies. Let's see, we had pennies and we had aluminum foil, and we put paper towel in between them to separate the electrodes. And we connected, Thomas was soldering everything, so he soldered all these pennies together, okay? And then we had aluminum foil that we broke little leaves off of, so they were all connected with little leaves, and we put a penny and paper towel, and then some aluminum foil, and paper towel, and then a penny, paper towel, aluminum foil, paper towel, and stuck that in salt water, and it worked. We had a little homemade battery. So if you're ever on a deserted island and you have pennies and aluminum foil, I don't know if y'all remember the show Gilligan's Island, but that was always the thing. They were trying to figure out how they could signal for help. So then now that we have a 1.5 volt cell, and it may not be the cheapest cell because it uses silver, and silver is expensive, but still, how do we make a 6 volt cell? Well, if you put these batteries end to end, the voltage is added. So each one of these adds 1.5 volts. So this is how you would get a 6 volt cell. It's putting them in series. And the way I think of this is like a waterfall. So if you have this pool of water down here and you have a little mountain stream and you have a waterfall. So this is water. Okay. And that's 1.5 volts. Putting a waterfall on top of a waterfall, you have the same sort of flow, but it's now at 3 volts high, right? You've doubled the altitude, and so the force is stronger on that water. It's way high. It's going to accelerate more and so on. And so that's what series gives you. If you put them in parallel, then you just have 2 waterfalls. You have twice the flow with the same force. So So this is parallel. You see why it doesn't double the voltage? And that's why multiplying those half reactions by a constant, like 5 or 2 or whatever, it doesn't change the voltage. It just adds more capacity. It adds more current, more electrons are flowing. But it's the metals and their interaction that give you the voltage. Here's some other kinds of batteries, like you've seen these little gasket batteries. Sometimes these gasket batteries have a little like a ring where air can get in there because oxygen is one of the reactants. So these are just some of the batteries that you have in your everyday life. Here's one of the most common batteries, your automobile batteries, which are lead acid batteries. I like to show this one because it's so common. Everybody pretty much has a lead acid battery in their car. They make lithium ion batteries, but they're really expensive. And so the lead acid battery, even though it's old technology, still pretty advanced and still pretty cheap and affordable. So it's super heavy, but your vehicle is able to carry it. So for like battery packs and portable devices, that's why we don't have lead acid batteries for our laptops. They would last a really long time, but it would just be incredibly heavy. So nobody wants to do that. So this is a very interesting reaction. If you look at it, the anode reaction is lead metal reacting with sulfuric acid to make lead sulfate, and that gives us 2 acid protons and 2 electrons. Those 2 electrons and protons are used by lead oxide at the cathode and sulfuric acid to make lead sulfate and 2 waters. So this is a really interesting reaction. When you add everything down, you have the lead and the lead oxide as your 2 electrodes, and they both react with sulfuric acid, make lead sulfate, and the product is water. Pretty cool reaction. The sulfuric acid is a reactant on both sides. So battery acid is as pure as sulfuric acid as you can get. And so that's available in every hardware store, that you can go get very pure sulfuric acid because it's battery acid. So that's also a problem in terms of, people being able to get concentrated sulfuric acid right there at the hardware store. But it's, like some of the batteries that are going to sit on the shelf for a long time come dry. Like motorcycle batteries come dry typically. And so you buy the box, you get home, you open it up, there's a little white container of sulfuric acid in the battery. You pop the little tops off and you pour the sulfuric acid in, and it's ready to go. But you've got people at home that don't know what they're doing handling concentrated sulfuric acid. So I don't know. I don't know what the statistics are on people getting it in their eyes or on their hands or pouring it down their, front of their pants or whatever in terms of their jeans. They won't know much until after they wash it and dry it. Then they'll have these cuts. So when I was in college and cut jeans were just becoming popular, I had some sulfuric acid from the CHEM Chem lab, true confessions, and I put my own little cuts in my jeans, which is great, man. They were like immediately frayed. You wash them and they were perfect. They didn't look like they were cut with scissors. And but then I don't know what the deal was, but like some of that compound, maybe the sulfates or something, were still corrosive because after 3 or 4 washes, the cuts kept getting bigger and bigger and bigger. So it totally trashed the jeans. But anyway, that was kind of fun. Now it's neat you can test the strength of the battery by testing how strong the sulfuric acid is. And as a kid, I remember being amazed at this. It was like an Everlast battery. It had the battery here, and inside the battery was a little tube, and inside that little tube was a fluorescent bead that was heavier or more dense than water, but not as dense as sulfuric acid. So whenever the battery was fresh, the sulfuric acid, that little bead would float, and it was fluorescent yellow. And you look in the top of the battery, it looked like a light. It looked like a little light, but it wasn't a light. It was just a fluorescent bead. You could see it when it was fresh. And then when it got to be more water than sulfuric acid, that bead would sink. And so you look in the little sight glass and you couldn't see anything. Now that was one of the most clever ways to determine if the battery was fresh or not. It was a density measurement. And so I still think that is so cool. They don't have that much anymore. Now you have to test the battery under load. You have to have some electronic gizmo that's going to measure the voltage. And I think this was such a fantastic way to test. Now you can still buy these little density meters that have a bunch of different beads in them, and you suck some of the battery fluid out of the top if you have a battery that can be opened, and certain beads will float and certain beads will sink, and you look at the color code and you say, okay, it's a fresh battery or not. Now notice if you run this backwards, you can charge it up. You can turn that water back into sulfuric acid. It generates heat and some of that water evaporates. So like on my trailer, it's constantly charging the battery and it's constantly evaporating the water. And so the water level starts to drop and I can't recharge the battery. You always have to add water or you'll ruin your battery. So these are some battery maintenance tips. I know this is PChem, but these are practical tips for lead acid batteries is you have to keep them filled with water so that they can recharge. And they'll last quite a while if you do that. But recharging them, because you're running this backwards, the voltage that you recharge it with is probably above the breakdown voltage of water. And so it's going to also electrolyze some of the water. That means it's building up hydrogen. And so you definitely, if you're going to have it on a fast charger, you want to have the tops off that battery and you want to have a breeze to keep that concentration of hydrogen gas low. So here's a picture of the spongy lead inside these little waffles of lead. That's why it's so heavy, because they have these lead waffles that are filled with the spongy lead oxide or the spongy lead. And again, this is an old battery invented in 1859. Seems crazy. Now let's move to what we call flow batteries. So most of the batteries we've talked about, and probably in your mind, most of the batteries you think about are like 2 electrodes. And when the electrodes get depleted, the battery doesn't work anymore. Okay. Well, what if we could continually refresh the reactants? That's what a fuel cell is. You may have heard of a fuel cell. It's just a battery, but you can add the reactants continuously. So as long as you're adding reactants, the battery is generating a voltage. That's fantastic. And this is one of the best ones, I would say, because you put in hydrogen and oxygen and you get water out. So this, I mean, that's great. If you have hydrogen and oxygen gas, you can put it through this fuel cell. Water is your only byproduct, and you get electricity out of it. Seems super safe. Well, hydrogen and oxygen, they're pretty hard to contain. And this is what caused the Apollo 13 to have the explosion, is they had oxygen tanks, hydrogen tanks. They were running these fuel cells. So this is, 1960s technology. But the real challenging thing is this proton exchange membrane. So the current is limited by right here. The speed at which you can conduct hydrogen ions through that membrane. And so they could get voltage out of their fuel cells back even in the Apollo days. These have probably improved a lot, but still that's the current limiting step. Why is current a big issue? Well, if you want to get an electric motor started or have some torque, you have to run a lot of current through those wires to generate a large magnetic field to turn the motor. And if the motor is resistant to being turned, the current goes up and up and up. And if it's not enough to turn it, then it's just generating heat. Now, if we run electrolytic cells backwards, if we run galvanic cells backwards, we have an electrolytic cell. And it's a way to turn electrical energy into chemical energy. Now, I talked about having oxygen and hydrogen. We don't really have a lot of hydrogen gas on the Earth's surface because we have an oxidizing atmosphere. So as soon as hydrogen is produced, eventually it's going to get hit with an oxygen molecule. It's going to react and will make water. Okay, so we don't have a lot of natural sources of hydrogen. But hydrogen is a great way to store energy. So if we have an electrical source, we can split water, which is abundant on the Earth, and make hydrogen and oxygen gas. And then we can use that. So what we're doing is we're turning electrical energy into chemical energy. We can also use this to take aqueous ions of metal and make them solid, and so that's where all of our electroplating comes from, chrome-plated bumpers and silver-plated jewelry, etc. And so this is super easy if we know the current and the half reaction and so on. So here's an example of silver being plated on jewelry, 10 amps for 30 minutes in a silver nitrate solution. It's just straight up dimensional analysis. 30 minutes to seconds, and then this right here is amps. 1 amp is a coulomb per second. So this right here is 10 amps. And then in terms of coulombs to moles of electrons, that's that Faraday constant. So this is F. And then once we have electrons, we go to the half reaction, and we can see how many electrons gives us so many moles of the metal. So that gives us a mole of silver, and then a mole of silver is 107.9 grams. So that we put 20 grams. That's a lot of silver on that piece of jewelry, but maybe it's big. It's a necklace or something. I don't know. 30 minutes is also a long time, and 10 amps is pretty high current. So we're just now getting into electrochemistry in my research group, so I'm learning a lot more about how to do it well. And yeah, a lot of these are in seconds per like thousandth of an inch thickness. Now, other electrochemical applications, we have that activity series. And what does that tell us? That tells us every metal in solution has a different voltage associated with it. Well, that's pretty cool. Maybe we could use that to determine things like, is this metal in this solution? So we can make ion selective electrodes. Now you've seen pH probes. That's an ion selective electrode. It's testing the amount of hydrogen or protons in that water. But we could make a sulfur probe. We could make a bromine probe or something like that. They can make these little ion selective voltage electrodes that you can put in, and you can calibrate with salt solutions or whatever, and then you can measure. Now, some of those are really important, like potassium. Where would be the most common use of a potassium probe? Can you imagine that? It is a micronutrient for plants. And so if you could measure the potassium content in your soil, you would know if you needed to fertilize or not. So it's a limiting reactant in the soil for plants. So whenever you look at a fertilizer, it has 3 numbers. Let's see. KPN or KNP? I think it's KNP. So potassium, nitrate, and phosphate. So K plus, NO3 minus, and PO4 3 minus. And so if we had electrodes for each of those, we could take a scoop of soil, I don't know, half a cup, 10 grams, whatever, put it in a small amount of water, slurry it up, and then put these probes in there, and you could tell if I needed to provide just nitrate, or if I needed just phosphate, or if I needed all 3. Okay. For your lawn at your house, you don't need to worry about that, because it's not that expensive to treat a half acre or an acre of land. Okay. But if you're a farmer and you're about to buy a truckload and you don't need to buy the potassium, then you can save a lot of money by doing soil samples. And so you go out and you sample the soil all around your property, and you're like, okay, I need to put more nitrogen right here, but I don't need anything else. We're worried about phosphate runoff. This is all environmental chemistry talk now. We're worried about phosphate runoff because it causes algae to grow in streams and ponds and lakes, stock tanks on your farm, and so on. And so phosphate, if you over apply the phosphate, then you damage your natural reservoirs by having these algae blooms. So a lot of times they're taking the phosphate out of the fertilizer And for residential use, that means we're over applying it because our grass isn't responding to the fertilizer because it's deficient in phosphate. So we end up adding more and more fertilizer thinking that's the problem, but the fertilizer just has potassium and nitrate in it. A lot of the Scott's products don't have phosphate. And so the Scott's products are more expensive. They're brand name. They don't have the phosphate. They're not doing what you need them to do. There's like an off brand called Triple 13 that has 13% of each of these. And that's the best to buy because you've got the phosphate. So I know you guys don't have lawns yet, but just a reminder in the future, you need all three nutrients for your plants to be happy. Okay. Now let's talk about, I mentioned electrical to chemical fuel, kind of running back like uphill in terms of the electrolysis situation. This is a figure that we're going to use off and on, but mainly in the last part of the course when we compare energy sources, sinks, and conversions. And these are all the sources and conversions on this chart. Okay. And let me just introduce it quickly. Over time on Earth, all of our energy has come from the sun. Okay. So we're going way back, and all of that energy has grown plants and been converted through photosynthesis into chemical fuel. And so we have all of these, we call them fossil fuels, right? So for eons, we have all of this photochemical or photosynthetic activity that has generated these layers of fuel, chemical fuel under the Earth's crust or in the Earth's crust. And that's where we get a lot of our fuel. Now we also have discovered the nucleus just in the past I would say in the 40s is when we really decided how to use it, or discovered how to use it for energy. So not even 100 years in the recent past, nuclear energy. So these are a couple of different sources. They can be converted. Like you can take that chemical fuel and burn it and produce heat. So you have thermal energy. Maybe that's what you want. You want to boil an egg, or you want to warm your house. So that's thermal energy. Maybe that thermal energy can be used to spin a turbine. And so now that spinning turbine is mechanical energy. And now we hook that turbine into an electrical motor and we generate electricity, or a generator. So this, you see how all the different types of energy are on this chart. Well, chemical fuel can go straight to electricity through a battery. And so that's where batteries fit in, batteries and fuel cells. And it's hard to really get a good hard number on the efficiencies of those. These are pretty good numbers. The steam boiler or gas furnace, 88 to 85% efficient. The steam or gas turbine, that's the thing that hurts us the most, is turning hot gas into mechanical energy. You think about a fan blade. It takes some of the heat out of that gas as it expands past the fan blade. But if there's any heat left in the gas, then you've lost those joules. So how can a fan suck every joule out of a hot gas? It's really hard. Only 46% of those joules get sucked out of that hot gas by the fan and turned into spinning motion. Now that spinning motion, turning a magnet inside of a bunch of coils, that is fantastic. We can get a lot of that spinning motion out as electricity through an electrical generator. Going directly from chemical to batteries might be better than this, or it might be worse. Most of the time now, using batteries, it's just a convenience thing, like your laptop or what have you. You don't want to have to put gasoline in your laptop, right? And have some sort of combustion motor in there. Now, combustion engines, they go with the pistons, go straight to mechanical since they're not spinning a turbine. So we have all these different efficiencies. Electrolysis, I have found one number that said it was around 72% efficient, so electrolyzing hydrogen and oxygen. And so going from electricity to make hydrogen and oxygen, we lose, 28% of those joules, and then coming back, if you have with a fuel cell, that's probably the most efficient at 40%, we lose another 60% of those joules. And so all of these percentages are multiplied. So every time you go through a step, they're all less than 1. So every one of those steps reduces the amount of joules that you make to the end. So if we take coal and make steam with it, we spin a turbine to make electricity. That's 0.88 times 0.46. You see, that's the one that hurts the most. Times 0.98 equals 0.4, so 40% efficient to get electricity from chemical fuel through steam. If we take that that electricity, that 40%, we do the electrolysis here, which is 72% and 40%. And so if we're using coal-fired power plants to electrolyze water and then use a fuel cell, we have 11%. So from the chemical fuel we started with to making some sort of fuel cell electrical powered battery, we've thrown away 90% of the joules we had in the coal. And so this is where I guess, and we'll cover more of this later in the course, but I do want you to think in terms of efficiency. When they talk about the efficiency, many times they're just giving you one of these numbers. Like they may say, this particular water heater or something is they'll say this, this particular water heater is 88% efficient, and that's fantastic, okay? But then they'll say this other one, it's an electrical water heater, and it's 90% efficient, so it's more efficient. But it's not if you are using coal to go all the way through this to make electricity and then using the electricity to heat water. You see, globally thinking, you need to do all of the efficiencies. So where are you getting the electricity? So a lot of these electrical appliances that they're pushing are efficient in the appliance, but where's the electricity coming from? If the electricity is coming out at 40% efficient, we've thrown away 60% of the joules. If we could burn natural gas to make that hot water, then we would have 80% of those joules being used. So we'll talk about that more later. Corrosion is a huge issue. It's also an electrochemical issue. So here we have O2 making this reduction of oxygen and oxidizing aluminum. And this is a very spontaneous cell. It's 2 volts. And so why don't aluminum cans dissolve? Well, the oxide coating stops further corrosion. So coating is really the key to stopping corrosion, keeping oxygen and the metal apart. So rusting iron is also very spontaneous, and the water drop will act as a salt bridge, and chloride will make it even worse. And so let's look at the rusting of iron. Let me just jump ahead here. So here's iron. Oxygen comes here, and it's reacting with the iron. The iron ions here are making the rust, and the electrons. You see, the electrons are leaving here, going to the oxygen, and creating iron cations, and those iron cations are reacting with this reduced oxygen to make the iron 2 oxide. And so you get 2 things happening. First, you see the discoloration of the surface, which you really don't like, right? You see this rusty iron part, that's not great. And then look at this is a pit. I'm going to say bad, okay? Because what do we make with iron? Iron is not really a very decorative thing. I mean, we have wrought iron, okay, that's fine. But we use iron for pipes, we use iron for, I-beams and so on. We don't want pits in our iron because it's going to weaken the structure. So one thing we can do is we can put a sacrificial anode on there. And again, using the activity series, we see that zinc is going to be more oxidizable than iron, and so the zinc will react first and make zinc oxide here. Zinc oxide, and so we might have some white powdery scale on our zinc coated parts, and so this is called galvanized iron. And the galvanized part, that word is used to galvanic cell, so they just electroplated zinc onto iron. So you can see this on the tin roofs and so on. They call them tin roofs, but it's really iron with zinc on top. Galvanized pipes are iron pipes with zinc on top. We don't see that very much anymore in terms of residential pipes because it's all plastic now, polyvinyl chloride, but you'll still come across galvanized metal. Now, some things structurally we need to use steel, and some things are in contact with ocean water. And so these anodes, you can buy anodes for galvanized pipes. If you have underground pipes, you have these little strips of zinc that you can just use a hose clamp and clamp it on, and it has access to oxygen. It'll protect the whole line of pipe. But if you think about deep sea structures, oil wells or pipelines, they make these huge zinc, magnesium, or aluminum anodes, and they weld them on to these structures. So here's one right here being shown to protect this deep sea structure. So this right here, this big square or rectangular structure is enormous, and it's going to be chewed up by the oxygen in the seawater. And that salty water is a great electrolyte, so this happens pretty rapidly, and so they have to come by and weld some more on and take the old ones off. And lastly, this is kind of like a phase diagram. We're not really going to get into interpreting them, but the reduction potentials that we have in that reduction potential table are pH dependent to some degree. And so you can map out all of the species on this chart that has reduction potential on the y-axis and pH on the x-axis. And notice it is kind of like a nice little phase diagram. If I'm at, say, pH 9 and potential of, say, 1.2, then right there the predominant species is lead oxide. But if I lower the pH, it might be lead sulfate. And if I sit right here, I'm at like a battery point where there's an equilibrium between lead sulfate and lead oxide. And so this would be the pH, the optimal pH for an equilibrium between those two species. Now, you also have the solvent, and so you're going to have a solvent window here that will limit your Pourbaix diagram. So if you're in water, then you go too high in voltage, you're going to electrolyze the water, and so on. So there's Pourbaix diagrams. Again, this would be for 1 molar iron solutions. Are just like a phase diagram to show you all the electrochemical species that exist at particular voltages and particular pHs. So that's all I have for the electrochemical line notation.